Feed me, Seymour. Feed me, Seymour! I'm starving! Your blood? Why, yes, I'm hungry, Seymour, but not for blood. It's some brain food, a little intellectual stimulation I'm craving. What do you say about some word problems for this poor, hungry little brain of mine to chomp on? Well, if Audrey 2 wills it, then so it shall be done. Welcome to Class 9.6, where today we'll continue our discussion of problem solving with quadratics, this time featuring some word problems. And if my goal is to solve a word or world problem, you'll hopefully remember from the many times we've done this before that we've got a 5-step potential best practice, a checklist that can help guide us through that process. Take 30 seconds, look back at your notes, refresh your memory. What are some of the things that I might want to keep in mind as I'm going from words to symbols? Go! Alrighty, we've done this time and time again. I'll save you the dirty details. So, to begin, if there's a visual dimension to my problem, it might be helpful to draw a diagram. From there, I need to define my variable. I need to know what it is that I'm looking for. If there's a particular relationship I want to use to my advantage, then a chart might be helpful, but maybe not. I definitely need some equation that I'm going to solve, and once I've got that equation, I just need to make sure, in context, does that answer make sense? Is it reasonable? With all of this in mind, let's try our hand at a problem like this guy. A conservationist has acquired the deed to a small tract of land, 4 acres in length and 7 acres in width. With permission from her local government, she plans to expand the ground's length and width by the same amount each, such that a total of 45 square acres of land will be under her care. By how much will she need to increase the length and width of her property? Now, we've solved some problems like this back in Unit 7. You might want to look back at your notes and refresh your memory. From here, either way, I want to know what's a good opening move, what is my variable going to represent, and how can I use the information given to me to write and solve an equation. Go! Alrighty. Well, the first thing that jumps out to me, I have a tract of land. It's 4 acres long and 7 acres wide. That immediately tells me that I should be able to start drawing a diagram in the shape of a rectangle. So I'll say here, right, my 4 maybe will be over here, and my 7 will be over there. I also know that this rectangle is going to get bigger. We're expanding the length and the width by some amount. We're not told what that amount is. In fact, it's what we're looking for, which means there should be our variable. I'll call it x. You can call it whatever you want, but I'll say this here, x, is going to be the amount that our friend is increasing her length and width by. I know that my ending unit is going to need to be in acres, so I might even tack that on at the end. From here, I know that I'm going to add a little bit to my length and my width, which we've called x, which in context is going to make that rectangle just a little bit bigger. The last piece of information that I have not yet used is that my total area is 45 square acres, which means there's an important formula that I need to know. What formula am I going to use to my advantage here? Go, 5, 4, 3, 2, 1. If you did not say that the area of a rectangle is equal to its length times its width, well, that's okay. We haven't done a problem like this in a while, but that means that I need to know the length and width of this big rectangle here if I'm going to use its area to my advantage. Well, I know that that area is 45, and to find the length and width, I just need to figure out, well, what's all the way up and down, and what's all the way left and right. Well, going all the way up and down, I've got that x over here, and that 4 over here. Putting them together would give me x plus 4. And then going all the way across, right, well, I've got that 7 here, plus this x over there. That would give me, if I write it in standard form, x plus 7. Now I know, doesn't really matter which one is the length and which one is the width, but when I multiply them together from the context of my problem, I should get 45. Beautiful. If you did not get here, that's okay. I'd like you to take 2 minutes, pause the video, and see how far you get in solving for x. Try it out, see what you come up with, and then come back and check with me. Go! Okay, from here, if I think back to those problems at the end of Unit 7, our first move was usually to get rid of those parentheses on the right side, because before I can factor, of course, I need a 0 on one side. So doing some met-wet over here on the right, I would show that 45 is equal to x times x, which is x squared. X times 7 is 7x. 4 times x is 4x, and 4 times 7 at the back is 28. I can combine some like terms on the right side to get that 45 is equal to x squared plus 11x plus 28. Now that my met-wet is done, I want to give myself a 0, right? Maybe I can factor it, but I also now have my handy-dandy quadratic formula that, in the absence of factoring as a potential solution strategy, could get me my answer as well. Well, x squared plus 11x minus 17, I hope you can see that this guy is prime. It cannot be factored. There are no two numbers that multiply to negative 17 and add to 11, right? 17 is prime. It can only be 1 and 17, which means that my handy-dandy quadratic formula x equals, say it with me, negative b plus or minus the square root of b squared minus 4ac all over 2a will be the trick here to get me out of this conundrum, which means I need to find some values of a, b, and c. Well, I'm in standard form. My leading coefficient here is 1. My b in the middle is 11, and my c constant term at the back is negative 17. Let's slot everything into place and see what we get. So I've got x equals negative 11 plus or minus the square root of 11 squared minus 4 times 1 times negative 17 all over 2 times 1. Simplifying, I've got negative 11 plus or minus the square root of 11 squared, which is 121. Negative 4 times 1 is negative 4. Negative 4 times negative 17 is positive 68, all over 2 times 1, which is 2. Simplifying even further inside of that radical, 121 plus 68 should be equal to 189, all of this over 2. Now, if I could, I would take the square root of 189, but 189 is not a perfect square, which means I need to find some factors that are. Notice that 189 is divisible by 9. 9 times 21 is equal to 189, and 9 is a perfect square, which means I can rewrite this using my product property as the square root of 9 times the square root of 21, and I can simplify the square root of 9 to reveal that negative 11 plus or minus 3 times the square root of 21 all over 2 is my final answer. And I'm done. Or am I? I'm going to give you a hint here. Our last step is to make sure that our answer makes sense. We've got two cases from the plus or minus. If you do your splittage here, can you tell me if either of these cases in the context of our problem doesn't make sense? What do you see? Take 30 seconds, take a risk, take a chance, who cares? Tell me something you notice. Go. Alrighty. Well, if I break this apart into its two component parts, I've got a plus case and a minus case. So either x could be equal to negative 11 plus that 3 root 21 all over 2, or it could be equal to negative 11 minus that 3 root 21 all over 2. Well, in context, because I'm working with length, if I look at the one on the right, notice that negative 11 minus something is going to get even more negative. The stuff on the right is a negative value of x. And I know that length cannot be negative. In context, that answer cannot make sense. For the one on the left, that means that negative 11 plus 3 root 21 all over 2 acres should be my final answer. And if I wanted to, if you're curious, I could plug this into a calculator. That would reveal that my value of x is about 1.37 acres, which absolutely makes sense. If I were to take the one on the right and plug it in, I would get a negative number. Again, length cannot be negative, so in context, this guy on the left is our only reasonable solution. Very nice. Let's try one more together, and then I'll set you free. We've had a bunch of long videos back to back. I'll bless you with a short one. At a community center, a kiddie pool 6 meters wide and 10 meters long, hey, that's a long kiddie pool, is surrounded on all sides by a deck of uniform width. The total area of the deck and the pool combined is twice the area of the pool alone. I want to know what must the width of my deck be. Alrighty, take a couple minutes, set up your diagram, define your variable, see if you can build me and solve me an equation. Go! Okay, well, we'll start by drawing our kiddie pool. We know that it's going to be, once again, a rectangle, and it's going to be 6 meters by 10 meters. I also know that on all sides, there is a deck of uniform width. Really quickly remind me, what does uniform mean? 5, 4, 3, 2, 1. Uniform means it's the same on all sides. So I've got around my rectangle a bigger rectangle that is the same distance across on all 4 sides. Now, I don't know what that distance is, right? That's what I'm trying to find, which tells me here that this length, which I'll call x, but you can call whatever you want, is going to be that width of my deck. If I'm thinking long term, notice that I'm in meters up above, so I might tack on that unit of meters at the back. So I'm going x here, across, 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 to build out the total footprint of my pool. The last thing that I'm told is that the total area of the deck and the pool combined is twice the area of the pool alone, which means I need to know what the area of the pool itself is. Well, the area of the pool, if the pool is 6 meters by 10 meters, its area, which I might write as area of the pool, is 6 times 10, which is 60. Because I am twice the area of the pool, let me multiply that by 2. So the total area is going to be 120 square meters. Slotting everything into place, using the fact that the area of a rectangle is equal to its length times its width, I should now be able to build myself an equation. Well, the area we've just found of our combined big rectangle is 120. I also need to know the length and the width of that big rectangle to slot in. Well, to get all the way up and down, I would need to travel x across from the deck, 6 across from the pool, and x across from the deck down there, which gives me 2 x's plus the 6 from my pool. All the way across, right, I go x across, plus a 10, plus another x. So I've traveled across 2 x's and a 10, which tells me that 120 should be equal to the product of that 2x plus 10 and that 2x plus 6. If you got here, amazing. And if you didn't, also amazing. Give yourself a little bit of time. Let's see if we can solve for x. Go! And stop. So from here, once again, we'll begin with a little net wet. So on the left, we've got our 120, and on the right, that should be equal to 2x times 2x, which is 4x squared. 2x times 6 is 12x. 10 times 2x is 20x, and 10 times 6 is 60. I need to combine those like terms over on the right side. So 120 should be equal to 4x squared plus 32x plus 60. My last move here, I want a 0 on one side, either to factor or to use the quadratic formula. So I've got 120 minus 120 is 0. And then I've got 4x squared plus 32x minus 60. From here, before I use the quadratic formula, do you see a quality of life choice I can make? Pause the video. What can I do to make my life easier? Well, look at all those numbers. 4, 32, 60. Let's divide everything by 4 to get some nice, friendly numbers. Well, 0 divided by 4 is 0. 4x squared divided by 4 is x squared. 32 divided by 4 is 8, so I've got 8x minus 15. Now, looks can be deceiving. This might look factorable, But in this case, there are no two numbers that can multiply to negative 15 and add to positive 8. Here's another case where my quadratic formula is going to come in clutch. I know that that quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. In our equation, well, a at the front is 1, b in the middle is 8, c at the back is negative 15. Let's slot everything into place. So x is going to be equal to negative 8 plus or minus the square root of 8 squared minus 4 times 1 times negative 15 all over 2 times 1. Simplifying as much as I can, I've got negative 8 plus or minus the square root of 64. Negative 4 times 1 is negative 4. Negative 4 times negative 15 is positive 60 all over 2. Simplifying even further, inside of that root, 64 plus 60 is 124. All of this over 2. Again, 124 is not a perfect square, but 4 certainly is. And 4 times 31 is equal to 124. So I can break this down using my product property. Here's negative 8 plus or minus the square root of 4 times the square root of 31 all over 2. I know that negative 8 plus or minus 2 root 31 over 2 is my simplified form here. And last but not least, notice that all of these coefficients are divisible by 2, which reveals that my final answer should be negative 4 plus or minus the square root of 31. The last thing that I need to do here, just like I did above, is some splittage. Because of this plus or minus, there are two answers hiding out. Either x could be negative 4 plus the square root of 31, or negative 4 minus the square root of 31. Again, if I were to think about this guy on the right, a negative minus something is getting even more negative. This is a negative length that don't make no kind of sense in context, which means that negative 4 plus 31 meters, which if I were to plug this into a calculator, would be about 1.57 meters, is my only final answer.